Hello, I am Shashank Agnihotri from the Chair of Machine Learning at University of Mannheim, presenting our work FlowBench benchmarking optical flow estimation methods for reliability and generalization recently accepted to TMLR. In the last 7 to 8 years, optical flow estimation has primarily been a deep learning based task. And as all deep learning based tasks go, the community has been improving the IID performance of these models in the last 7 8 years, which is what we can see here in the plot on the left. And then comes reliability and generalization ability. So reliability here is reliability under adversarial attacks, and generalization ability is generalization to out of distribution samples. And now what we do is we take all of these methods that have been proposed in the last 7 to 8 years and we benchmark them under adversarial attacks and we benchmark them under OD corruptions. And what we observe is that all of these models do not really improve the reliability or the generalization ability significantly. The exact metrics of NARE and GAE, I will be explaining them later, but essentially for understanding here, these are still the EPE values. And as you can see, the EPE values are super high both for reliability and generalization. What we would ideally want is a low EPE, because a low EPE is good and a high EPE is bad. Many prior works have proposed adversarial attacks like COS-PGD, PCFA, adversarial weather, and methods to gauge the generalization ability of optical flow estimation models. And these are very essential to make sure that the optical flow estimation models can be used in the real world in a reliable manner. And in this scenario, white box adversarial attacks play a very crucial role as they help us understand the vulnerabilities of these models, whereas benchmarking these models' common corruptions help us understand the generalization ability of these models. However, the issue that the community faces is that there is no one single framework where we can evaluate all of these for all optical flow estimation methods for all given data sets. And that is where we come in. We propose FlowBench. This is a benchmarking framework and a benchmark for optical flow estimation methods benchmarked on adversarial attacks and common corruptions. What you see here is the overview of FlowBench, in which you can select multiple data sets, you can get the optical flow estimation method, you can load the weights of the model trained for the respective data set, and then what you can do is you can get the respective images from these data sets, you can either adversarially attack them or you can add synthetic common corruptions to them to corrupt the images, and you evaluate the models on these and you finally get the benchmark FlowBench that we have evaluated. In our benchmarking, we have benchmarked almost all possible optical flow estimation methods for which we could find checkpoints for both Kitty and MPS Intel. However, we do also have checkpoints for Flying Things 3D and Spring, and you can also add your own checkpoints to this benchmark. Just in case you only want to query the results, then we have them for Kitty and MPS Intel in our benchmark for all of these models that are listed here. From the benchmarking that we did, what we obtained is a tabular benchmark, and it can quite easily be queried using the libraries that we make publicly available. And the usage is very simple. For example, for an adversarial attack, all you have to do is define the model name, the data set that you want to use, the threat model, meaning the exact adversarial attack, COS-PGD, PGD, FGSM, BIM, PCFA, adversarial weather. We have all of these covered. And then the number of attack iterations that you want to use, the attack step size that you want to use, the perturbation budget that you want to use, then the LP norm constraint to be applied, L infinity or L2, and then if the attack is targeted or non-targeted, and then how do you want to optimize the adversarial attack? Do you want to optimize it with respect to the ground truth, or do you want to optimize it with respect to the initial flow? This is also something that we come up in our FlowBench, which I'll be explaining later. And then finally, there is a flag for retrieve existing, which would just retrieve the results from our tabular benchmark. If set to true, if set to false, then it will perform the evaluation for you. So as you can see, the benchmark is very easy to use and very user friendly with a lot of documentation on our GitHub. The link I'll be sharing towards the end. The objective of our extensive benchmarking, the largest ever for optical flow estimation methods yet, is to gauge the reliability and generalization ability of these optical flow models. To do this, we ask the question, under a threat, what is the worst possible performance of a given method? Now, what this means is we take a model for a data set and we attack it with all possible adversarial attacks with similar budgets. And then we take the worst performance from across all of these attacks. Then the same thing is what we do for generalization ability. We corrupt the images with all the 23 common corruptions, 15 2D common corruptions, and 8 3D common corruptions that we have considered. And we take the worst performance across all of these, because what we want is our worst performance to be better in the real world. However, we also benchmark the endpoint error, we benchmark outlier error, we benchmark cosine distance, 1px error, 5px error, 3px error, and then to make an analysis at a large scale, we also have a metric which is a wrapper around EPE, as explained in the previous slide. We, for adversarial attacks, for targeted adversarial attacks, what we do is we have this metric called TARE, and the notation is TARE, and the superscript is the target vector that we are using, and the subscript is the number of attack iterations used to optimize the attack. Very similar for the non-targeted attacks, and something very similar for generalization ability, in which it is the worst EPE across the 23 common corruptions that I spoke about in the previous slide, and we note it as GAE, with the subscript being the corruption severity level used, and we make sure that we use the same severity level across the 23 corruptions while benchmarking. So from all of these benchmarking, we found some very interesting observations, and we made these observations across 57 checkpoints for Kitty and MPI Centel, 3 data sets, Kitty, MPI Centel, Clean, MPI Centel Final, and then we have 9 diverse adversarial attacks: FGSM, PGD, BIM, COS, PGD, PCFA, adversarial weather, which includes fog, snow, rain, and spark, and then the 23 established common corruptions, both 2D and 3D. And now we discuss the important findings or the main takeaways that we had. One of the first takeaways that we would like to discuss is targeted versus non-targeted attacks. So here what you see on the y-axis is targeted attacks, on the x-axis is non-targeted attacks, and over here when the target vector is 0, and here when the target vector is the negative of the initial predicted flow. So what we can observe is that there is no real clear correlation in the performance of the non-targeted and targeted attacks, irrespective of the target being used. However, in the case of targeted attacks, there is a very high correlation between the two targets that were used, that is 0 vector and negative of the initial flow. And this is interesting because now this helps the community not having to benchmark their models on both the targets but just one of them. And another interesting observation that we made is this method IRR, which is PWC with iterative refinement, and this performs quite well. So as discussed earlier, since what we're looking at is essentially error, a lower error is better, and that is what we observe here, that IRR is performing significantly better than almost all the other optical flow methods against adversarial attacks. The second crucial observation that we like to discuss is something that helps the community a lot, because while optimizing white box adversarial attacks, there's always the need for ground truth annotations or ground truth flow. However, in case of optical flow, unless the dataset is synthetic, it is very difficult to get ground truth flow, and therefore optimizing white box adversarial attacks can be a bit cumbersome on real world video. However, what we observe is that if we use the initial predicted flow instead of the ground truth flow to optimize the adversarial attack, then the relative performance, and in our case, very interestingly, also the absolute performance of the methods is very similar. So there are 1 or 2 exceptions here and there. For example, GMA in these plots that has a shift in its absolute and slightly relative performance. However, on a large scale, to gauge the relative performance of an optical flow method against white box adversarial attacks, one can use the initial flow. Next, what we try to look at is the performance of a family of methods. So the definition of a family of methods is slightly vague here. However, what we mean to convey here is one method that was proposed that was monumental, and a lot of other methods incremented upon the monumental method until a new monumental method came out. For example, people started with FlowNets and then moved on to PWC and then moved on to something like Raft and then something like FlowFormer. And now there are a few other methods coming which do not really fall into one of the families, so we just give them another family of its own. These include SSR flow and deep inverse patch match. And What we observe is, for example, flowformer methods, which includes flowformer and flowformer plus plus, both being transformer based methods, they are not more robust than the other family of methods. So their clean EPE is amongst the best, as you can see here. However, they are not so great when it comes to non-targeted adversarial attacks or targeted adversarial attacks or generalization ability. This is a contradiction to the observation that is usually made in the image classification literature and to some extent semantic segmentation literature as well, where transformer based methods are inherently more robust than other methods. However, this is not something that we observe for optical flow methods. Our next study is also motivated by literature from image classification that shows higher model capacity might lead to better robustness. However, in the case of optical flow estimation, as you can see from all of these plots, where the x-axis is the number of learnable parameters and the y-axis, the first plot is clean EPE, then the non-targeted adversarial attacks, then targeted adversarial attacks, and then finally robustness to common corruptions. There is no such correlation which shows that increasing the number of parameters will definitely lead to an increase in performance, which is again quite interesting. And then finally, what we try to do is we try to find a correlation between IID performance, reliability, and generalization measure. What we observe is that there is no correlation, which is quite interesting because in a lot of scenarios, we do observe correlations. For example, in semantic segmentation and image classification, we observe some correlation between clean performance and OOD performance, like performance towards common corruptions. However, that is not the case here in optical flow methods. Summarizing, FlowBench is the first unified benchmark for optical flow estimation methods to benchmark the reliability and generalization ability, and it reveals critical gap. Firstly, the obvious one, which is high IID performance does not imply robustness, and it is an open source tool to help the community evaluate, compare, and build more dependable optical flow methods. And everything is on GitHub. And for future work, we would like to extend FlowBench to new data sets, patch attacks, black box threats, and more real world corruptions to better gauge the performance of these methods in the real world. And of course, we are open to collaborations with contribution of checkpoints or attacks or metrics or new evaluation ideas. And of course, the things that we have planned as an extension. Any collaboration there is welcome. Following are some useful links. The first one is the project page, where we have similar other benchmarks for semantic segmentation, object detection, disparity estimation, and second is our GitHub. Everything is open source. Please let us know if you face any issues. Finally is the paper that was accepted at TMLR. It's an interesting paper. Please read through it. It has a lot of documentation as well of how to use FlowBench. So I leave you on this note with our amazing visualization of attacks and corruptions and the optical flow estimations for them. Thank you all very much. Oh, thanks for staying until the end. Goodbye.